Problem 91 gives a tensor stress S with its principal values sigma 1, 2, 3 with corresponding principal directions n1, n2, n3. And there is a plane parallel to n3 given as M, like this. And first, the question asks us to show that the traction vector and its normal components are given as T sub M and sigma theta. Second part is to show that the shear and the normal components of the traction vector satisfy the relationship as this. And then we are given sigma bar and rho, and we are asked to show that the shear and normal components of the traction vector satisfy the relationship as this. Okay. Part 1, to show that the traction vector T sub n equals to sigma 1 cosine theta n1 plus sigma 2 sine theta n2. And the normal component sigma theta equals to sigma 1 cosine theta squared plus sigma 2 sine theta squared. Using the spectral decomposition, we have the tensor S equals to sigma I ni tensor ni. The traction vector equals to S operating on M. We have sigma I ni tensor ni operating on cosine theta n1 plus sine theta n2. Then we have this equation cosine theta sigma I ni dotted with n1 times ni plus sine theta sigma I ni dotted with n2 multiplied by ni. And that gives us cosine theta sigma I ni delta I 1i plus sine theta sigma I ni delta 2i. We know that only this term is only non-zero only when I equals to 1, and this term is non-zero only when I equals to 2. So we have the equation as sigma 1 cosine theta n1 plus sigma 2 sine theta n2. And that's for part 1. Now part 2. Sigma theta is given by M dotted with T sub M. And that is cosine theta n1 plus sine theta n2 dotted with sigma 1 cosine theta n1 plus sigma 2 sine theta n2. And n1 dotted with n1 is equal to 1, and n2 dotted with n2 equals to 1. So we get sigma 1 cosine theta squared plus sigma 2 sine theta squared. So second part is proved. Okay, step 2, we're asked to show that tau squared plus sigma squared equals to sigma 1 squared cosine theta squared plus sigma 2 squared sine theta squared. By definition, tau is given as this, so we get the tau squared equals to the length of the traction vectors squared minus sigma squared. So tau squared plus sigma squared equals to the length of the traction vector squared, and we already know that the traction vector is given as this. So we got tau squared plus sigma squared as sigma 1 squared cosine theta squared plus sigma 2 squared sine theta squared. So second part is proved. Step 3, we are given that the sigma bar is half sigma 1 plus sigma 2, and the rho is half sigma 1 minus sigma 2. It asks us to show that tau squared plus sigma 1 minus sigma bar squared equals to rho squared. From this equation, we get tau squared plus sigma squared minus 2 sigma bar plus sigma bar squared. And that we substitute we already know that this part equals to this. And then we substitute sigma bar into this equation. We got this. And then we multiply every item in this part. We got this equation. And this item cancels with it. And these two cancel each other. And this one goes to 1. We got this equation. Then finally we can write this equation as this form, which is equal to rho squared. So the last part is proved.